Okay, good afternoon, everyone. Welcome to the June A3D3 seminar. It's my great pleasure to introduce our speaker today, who's Thea Aarrestad. Thea is a research fellow at ETH Zurich and a member of the CMS collaboration at CERN. She got her PhD in physics from the University of Zurich and then spent 2 years as a research fellow at CERN before moving back to Zurich as an SNSF Ambizioni grantee. Her research centers on how machine learning can be applied to particle physics problems, especially focusing on utilizing real-time machine learning for discovering new physics phenomena. So it's, very, very well aligned with the A3D3 interests. And she's going to be talking today to us on leveraging real-time machine learning for handling massive LHC data streams, which is a subject I'm particularly interested in hearing about. So without further ado, Thea.
Thanks a lot. Thanks for the introduction. I noticed another thing I'd like to get rid of with this, which is getting this single page. And then I promise I'll start. The single page.
Hello.
Oh. Hello. Let's see. Is there something else I need to do here? Single page. It's already full screen. Okay, you'll just have to live with the kind of split thing at the bottom. So again, thank you very much for having me. I'm really, really excited to be here and talk about what I work about every day, which is using machine learning to handle big data at the LHC. It's a great pleasure. I've heard a lot about A3D3 and you do a lot of really interesting stuff. So I wanted to start with a little bit general. Usually when I talk to colleagues here at ETH, they're usually in the chemistry department or biophysics. And when we talk about AI, we usually talk about these enormous models that can do fantastic things. And they talk a lot about AI for accelerated discovery, for instance. And I think AlphaFold is just the most fantastic example of this. So where you're trying to predict how proteins will fold simply based on the amino acid they consist of, which really defines their function. And in our body, we only knew roughly 17% of the 20,000 proteins we have within us. And after AlphaFold, this AI that can predict the folding of proteins, we have more than 98% of the amino acids in our bodies now mapped out. And this really allows us to discover new forms of medicines, treatment, etc. So this is a massive contribution of AI to science. And then we also have more kind of daily things that we talk to our grandmothers about, for instance, GPT, what it can do. Now it can take visual input. For instance, you can give it a picture of this smartphone and ask what's funny about this image, and it will accurately say, the humor comes from the absurdity of plugging a large FPGA into a modern smartphone. And big players in the machine learning game like Hinton, is also kind of starting to think about whether these things are really just statistical parrots or if they can do some form of reasoning based on their world model. You can also give GPT-4 charts and it can reason about it. You can upload, for instance, a chart with some data and ask it to sum or subtract and figure out things. So this is obviously fantastic. And why am I bringing this up in a talk about fast real-time machine learning? Well, the reason is that, yes, these models are fantastic, but they're also enormous. And a lot of their performance, their performative power comes sheerly from their size. So we know that GPT-3 was almost 175 billion parameters large, which roughly corresponds to 0.16% of the neurons in your brain, which doesn't mean that that's a direct translation, but that's roughly the size. And we don't know the size of GPT-4, which is currently the version running, but we think it's roughly 3 orders of magnitude larger. So basically corresponding to all of the neurons that you have in your brain. And the thing with these big models is that they are big. So for instance, OpenAI, in order to just train this thing, had their own supercomputer from Microsoft consisting of almost 300,000 GPU cores, 10,000 GPUs, all connected with high-speed 400 gigabytes per second network. And even then, it was trained for several weeks on roughly a 25-kilometer high book of text. So this is already creating sort of an inequality gap, because who can afford such a computer to train such powerful models? There's very few players in the game that can do that. And at inference time, when you're prompting GPT for something, we don't really know where that model is running, but it can't run on a single GPU because it's simply too big. So if we look at the size of GPT, if we would run the model with floating point 32 precision, it would use roughly 700 gigabytes of memory, which is an order of magnitude larger than the max memory we currently have in a single GPU. We do know that GPT-3 at least was quantized to floating point 16, reducing the size to 350 gigabytes or so of memory only for the parameters themselves, which still would mean you would have to invest in 10, 11 high-end GPUs for a price tag of $10,000 or so each, or more expensive GPUs like A100 for $50,000 and $20,000 each. And this trend is general. If we look at the size of deep learning models, so here in blue, you have some computer vision models. Here in red, you see these transformer-based architectures. These models are growing really, really fast. So the transformers are growing roughly by a size of 240 every 2 years, whereas the hardware memory that we have is only growing by roughly a factor of 2 or so every 2 years. And here you can see this V100 that you would need 10 of to fit GPT. So at this point, efficient inference, efficient deep learning is no longer becoming a choice because it's becoming expensive running inference, time consuming. And everyone currently working on deep learning is really especially these large language models, really starting to explore how we can make these models more data efficient and more efficient when it comes to inference time and also training time. So what does this have to do with the Large Hadron Collider? Well, whereas OpenAI GPT runs inference on 11 interconnected GPUs, and they have when you're waiting, you wait roughly 4 to 10 seconds maybe to get an answer. At the Large Hadron Collider, we currently have to do inference on single chips, and we have to do so within a few nanoseconds of time. In fact, if you look at it more in detail, and I really love this plot also from A3D3, if you look at how much data goes through our system at the Large Hadron Collider here on the y-axis versus how fast we have to be to process that data on the x-axis, you see that we're really in this extreme high throughput, low latency domain. And we also, judging from the size of each circle, have to process way more data than, for instance, what goes through Google Cloud or Netflix. So we have a lot of experience handling huge streams of data, and we're currently gaining a lot of experience in pioneering how we can do real-time machine learning on that data. So where's all this data coming from? So here you see the Large Hadron Collider. This is the CMS detector, the experiment where I work. And there currently we're colliding bunches of protons. So 10 to the 11 protons in bunches spaced with 7.5 meters. These bunches cross each other in the center of the detector, and every time these bunches cross, you have roughly 65 proton pairs that collides for every single crossing. And every time this happens, the protons kind of vanish, their energy is turned into new outgoing particles that traverse the detector and generate signal inside our experiment. And we have roughly 1 billion collisions occurring per second with a size of roughly a megabyte each of data due to the sensor information, generating a petabyte of data or so every single second. Now, why are we doing all this? Well, the reason we're doing that is to study the fundamental building blocks of matter, which are described in the standard model of particle physics. We have quarks, we have leptons, we have the force carriers. And all of these particles, their masses span a huge mass range, so 9 orders of magnitude between the heaviest particle and the lightest particles. And we want to measure all of them, which means we want to detect all of them, which is why we have detectors consisting of a lot of different types of materials. And they're also absolutely enormous and have many, many readout channels because we really want to measure all of these things with these big mass range and different type of interactions. So here, now my nice GIFs are unfortunately broken. So here you can see a slice of the detector. So you have the proton pairs colliding in the center and the new particles sort of traversing the detector material. And if we're looking for a particle, let's say a mu1, we can use information from all the subdetectors to say that it is a muon, and also to say what its energy is and other parameters. So we, for instance, know that a muon leaves signals in the muon chambers out here, and they also leave signals in the inner tracker. And we call combining this information in this way particle flow. And if you want to detect quarks, for instance, we know that they will leave a signature in the tracker and also dump all of their energy in the Hadron Calorimeter. And one of the first things we wanted to do when we switched on the Large Hadron Collider was to find and detect the Higgs boson, which was also predicted by the Standard Model in the 60s, but not yet discovered. So what we wanted to do was, for instance, look for the Higgs boson, and it lives for a really, really short time. It then decays to 2 Z bosons, which then further decay into leptons. And what we wanted to do was then collide protons many, many times, measure the energies of these lepton pairs. Here you see a candidate of a Higgs being produced, then decaying to 2 Z's, which decays to lepton pairs. There are electrons in green and a pair of muons in red. And then what we want to do is basically, well, now you can see also this GIF, unfortunately, is that we collide protons billions of times, and we see events basically accumulating until you have a peak at roughly the Higgs mass. So we have billions of collisions and then roughly 10 signal events, which will then be a discovery, and that's what we call a discovery. Okay, so what's the problem here? Well, every single time we do these proton collisions, we generate these enormous amounts of data. That's simply far too much data to all read out and store. Now, luckily for us, we don't have to read out all of that data and store it. And the reason for that is basically quantum mechanics, a game of probabilities. So if you look at the y-axis here, the probability of producing any sort of collision at the Large Hadron Collider, the probability of producing a Higgs boson is only 1 in a billion collisions. So even if we could, saving all the collisions wouldn't even be useful. So that's why we have a real-time event filtering system at the LHC to get rid of some of the uninteresting collision events. So here you see another vision of the Large Hadron Collider. Here's the experiment I work, CMS. It's roughly 100 meters underground, where we have these enormous amounts of data produced. Now, in our dream world, we will read out all of this data every 25 nanoseconds, send all out to big computer farms, reconstruct everything, save it, and then sift through it in all the time we have available to do whatever we want to do. The problem is that if we would want to read out all of that, we would need huge computer farms to process all of that data, meaning we would need a lot of money. But that's a kind of a trivial thing. You can get more money and you can build huge computer farms. The problem is we would also have to get all of that data out of the detector. And here we're in a little cavern deep underground with a lot of sensor detecting material. And in order to do that, we would have to supply this detector with a lot of power and a lot of cabling to get the data out. And that means we would have less active detector material, just due to the sheer amount of extra material we would have to put inside. So what we do instead is that every time a pair of protons, or one of these bunches, 2 of these bunches of protons cross each other, we buffer the data temporarily inside the detector electronics for roughly 4 microseconds currently. Then we take a subset of that data, 2 terabits per second, and we send that to something we call the level 1 trigger. The level 1 trigger consists of roughly 1,000 FPGAs, and they have the job of deciding which events to keep and which events to reject, all within 4 microseconds. And the task here is to reject more than 98% of the collision events, so we don't have to read out this petabyte of data per second, basically at a 40 megahertz rate. So the level 1 trigger will look at this subset of information and say, yes, this looks like an interesting event that maybe has a Higgs that decays to 4 leptons, or no, it's not interesting. And it sends a signal back to the detector and it says, okay, I want to reject this event. It doesn't look interesting. Then the pipelines, the buffers here are flushed and the data is gone forever. We'll never see it again. If the level 1 says, this looks like an interesting event, I want to look closer at it, only at that point do we read out the full detector. So all of the data leaves the detector and it's sent up through this shaft here. at a rate of 100 kilohertz, or currently 110 kilohertz. So it's now been reduced from 1 collision event every 25 nanoseconds to roughly 100,000 events per second that are sent out of the level 1 trigger. Now we still have terabits per second of data, so we need to reduce this even further. So at the surface, right above the experimental cavern, we have the high level trigger, which consists of almost 30,000 CPUs and now 400 GPUs. Here we have 300 to 400 milliseconds, because there's less back pressure. We've already reduced the rate to reject further 99% of the events coming from the level 1. Only after the high level trigger accepts the event do we read it out now at roughly 1,000 collision events per second at a throughput of gigabytes or so per second. Do we read out the full data, reconstruct everything, and store it? So we roughly have 0.0025% of all the collision events remaining. That means that this plot, which is the one you should have seen in the very beginning of the Higgs peak here above some background of events, to do these sort of analyses and say we've discovered the Higgs boson, we want to make sure that the algorithms that selects that data is really, really fast so we can get more data through the system and really accurate to select the right data, because Higgs, again, has produced 1 in a billion events. So now you can say, okay, that's great. The LHC, they did all this. They want to discover the Higgs. What do we do now? We discovered the Higgs already. Well, we know that the standard model of particle physics isn't the end of the story. And the reason is that a certain thing it can't explain, for instance, why these feebly particles called neutrinos have mass. We can't explain why the Higgs boson that we eventually found is so much lighter than what we would have expected it to be. And we don't know what most of the universe consists of. We don't know the nature of dark matter in the universe. So we need new physics. And if it exists, which it has to do, there's 2 ways to uncover it at the LHC, if it's discoverable at colliders. One of them is doing very precise measurements of certain physics processes. And another one is direct observation of new particles. Now, I said the probability of producing a Higgs is 1 in a billion. The probability of producing a new physics type of particle is 1 in a trillion, if at all. So that means if we want to see these processes, we need way, way more data. So in order to get way, way more data, we're upgrading the Large Hadron Collider. So starting in 2026, we will upgrade to something called the High Luminosity LHC. So what that will give us is a factor of 10 increase in the data size, and we'll have roughly 3 times more proton-proton collisions every second. And the way we're going to do that is by increasing the number of protons per bunch. Remember, we had these big bunches of protons, and also squeeze those beams of protons more at the point where they're supposed to cross each other, because most of the thing in those bunches is just air. We need them to be quite dense. So that's great. We will have more data. We will find new physics within a fraction of a second. Unfortunately, it's not that easy. We'll have more collisions, which means we'll have a huge increase in data complexity in the future. So currently we have these 65 proton pairs colliding every bunch crossing, every time the bunches basically cross. And in the future, we'll have up to 200 such collisions every time the bunches cross. So we have a huge increase in event complexity, and we need to detangle that because we don't want to lose on the physics, right? So we want to know what all of these are. We have to reconstruct them. So in order to better detangle these things, we're going to get more granular detectors. So for instance, CMS is investing in a very highly granular calorimeter. So that means we're increasing the readout channels of that detector, which currently has 85,000 readout channels, to 6 million readout channels in high luminosity LHC. So you have more collision and we have more readout channels. Now, what that will eventually culminate in is that we're going to need far more compute. So if you look at the total CPU needs we're going to have as a function of the year, this is where high luminosity LHC will kick in. We see that the compute need will increase significantly, whereas the total amount of resources that we will have, even accounting for an increase of 10 to 20%, we won't be able to cover that need. So we're going to need a lot of innovation and new techniques just to maintain the physics reach that we currently have when we're going to generate so much more data. So the algorithms we have today won't be sustainable in high luminosity LHC, and we want to look into using machine learning to become faster, better, and to do more. So high luminosity LHC will be a big challenge for us, and it is a place where we really have to do a lot of R&D into new algorithms. And the things that will change is, for one, we'll have these more collisions and more readout channels. To detangle them and be able to still select good data in the level 1 trigger, we will increase the amount of data flowing into the level 1 trigger from 2 to 63 terabits per second. Now there's so much more data, so we're going to increase the time we have available here from 4 to 12 microseconds. And since we want more data, we're also going to let more data escape the system and go to the high level trigger, and finally to be read out for full reconstruction. And due to the different requirements we have in these systems, so at the high level trigger, we have these 300 to 400 milliseconds. We use different type of hardware. So in the high level trigger, we use software, CPUs and GPUs. In the level 1 trigger, we use firmware, so FPGAs. And inside the detector itself, we use ASICs. And what I want to talk about here today is the inference we're looking at for on GPUs, so at the high level trigger, on FPGAs in the level 1 trigger, and on the detector itself. So we have some strict constraints for these algorithms. One of them is that they have to have an extremely low latency. We have proton-proton collisions occurring every 25 nanoseconds, and that's fixed and unchangeable. Secondly, we have a lot of algorithms running in parallel on the same device. So that means we're going to have to use very little resources and be very efficient with our compute. Thirdly, we're going to have to be really power efficient. So a lot of the inference we're going to do is going to be inside the detector itself, which often has limited power and is often cooled. Also, for the level 1 trigger, we're deep underground, so cooling and power is challenging. So we want every algorithm running there to be as minimal as possible. So we have this extreme combination of low power, low latency, low resource, and high accuracy constraints. So one of the things we're going to have to do in high luminosity LHC is to get this increased amount of data basically out of the detector. We have far more readout channels, more collisions taking place, and we need to get that out of the detector and into the level 1 trigger. So I mentioned before, we have this high granularity calorimeter with 6.5 million readout channels. It has a stack of layers so that we basically have a 3D imaging calorimeter, and we also have timing. We know when it entered and when it left, basically. So we have a 3D imaging calorimeter with timing. Unfortunately, we have a lot of readout channels, but we cannot read out all of these channels fast enough for the level 1 to trigger. So one of the things we're looking at is how we can use machine learning to compress sensor data. So as an example here, I'll use the high granularity calorimeter, but this generalizes. So for the high granularity calorimeter, we need to compress the data on the detector. So we're inside in a high radiation environment, cool to minus 30 degrees. And we have these ASICs on the sensors themselves to reduce and transmit the data. One, to transmit the data to the trigger, the level 1 trigger at 40 megahertz. And a second one to send the data that's selected up above the experimental cavern to the surface at 750 kilohertz. So we need to somehow cluster all of these channels in some way. Currently, we're doing it classically in a way of just summing nearby channels. But we're also looking into using autoencoders for this. An autoencoder learns to take some input and then compress it to some lower dimensional embedded space. So it's kind of like dimensional reduction, principal component analysis, and then decoding it again based only on that information. And a way that can be used for compression is, I guess, obviously, because now you have all of this information in this bottleneck. What we want to do is inside the detector itself, compress sensor data, and then only transmit that encoded data, which now occupies obviously way fewer bits than the original data. And then once we have transmitted the data, only then we can recreate the original data again, or do whatever operations we want to do on that encoded data. That's something we're exploring at CMS and also something they're exploring at LHCb for data compression. Then once we have the data out, we're currently in the level 1 trigger, this FPGA farm. And here you can see a little bit what that looks like. Here we again have the FPGA farm. This is what it looks like. We have a bunch of custom boards equipped with FPGAs. Here you can again see this slice of the detector, and we have a stack of FPGAs dedicated to very specific things. So for instance, we have 400 FPGAs just to do calorimetry, 50 of them for this high granularity calorimeter only. We'll also have tracking, which is something new in level 1. We need it since we have so much more complexity. We need it really to disentangle the events better. And then for muons, we have roughly 100 FPGAs. So you see also here that even though the whole system has 12 microseconds, this is really kind of serial. So these things have to be done before the next thing can happen. And so per algorithm, we roughly have 100 nanoseconds up to maybe 5 microseconds. We also then combine all of the information here, where we do kind of this particle flow we talked about before. Then we have the final bottleneck that makes the yes or no based on all the information that was done previously. So there's a lot of new things that's going to happen in the level 1 trigger for us, and a lot of tasks that will require a lot of compute. So why are we even using FPGAs at the LHC? Why aren't we using, for instance, GPUs or CPUs? Well, one of the reasons is that FPGAs can be programmed to be highly parallel. So you can either work on different parts of the problem, things that can be done in parallel, use all of the resources you have, but you can also work on different data simultaneously. So when one, for instance, proton collision event comes in, you can, before that's done, you can start working on the next and the next and the next. So you have a really, really high bandwidth, and you can really tune the granularity really flexibly. Secondly, FPGAs are, and some people discuss this, really power efficient. They can be up to a factor of 10 more power efficient than GPUs, for instance. And even with our current FPGAs, they dissipate a heat of 7 watts per square centimeters while processing roughly 5% of the total internet traffic. So these really need to be highly efficient. Secondly, and most importantly, is that they're really latency deterministic. So whereas every time you run a program on your CPU or GPU, you can have some event level interrupts, maybe some process takes X millisecond, the next time you run it, it goes faster or slower. The FPGAs have a really repeatable and predictable latency, which we need because we know every 25 nanosecond, there's going to be a new collision coming in. So what are FPGAs? FPGAs are field-programmable gate arrays, and they are exactly that. They are resources that have interconnects that you can reprogram. So whereas an ASIC is wired and it can do that function only, the FPGA you can reprogram as you wish. And the resources it has is memory. It has logic cells that can do arbitrary functions and also serve as a small memory. It has digital signal processors that are specialized units for multiplications. And then it has some really important resources called flip-flops. Flip-flops, their job is basically to hold on to the data and only release it at a certain clock signal. That means that it will wait until the exact right nanosecond before releasing the data to the next step, meaning everything is highly synchronized. So if you want to program such an FPGA, it requires some expertise. And the way you usually do it is that you write some C++ code decorated with some constraints or directives. You then pass that code to a compiler. And depending on which FPGA you have a different compiler. So for instance, in CMS, we have Xilinx FPGAs, and they offer a Vitis or a Vivado HLS compiler. That compiler takes your C++ code with some directives, so be more parallel, be less parallel, use more resources, use this resources, etc. And it translate that into a hardware description language that then can be used to generate a firmware block. Now, if you want to write highly efficient algorithms for instance, the level 1 trigger, it requires a lot of expertise because basically we have to deploy things in really busy devices, and we only have microseconds or nanoseconds to basically run inference. So the algorithms need to be really, really tuned. And translating neural networks into really efficient firmware blocks, it's not a lot of tools that can do that for you. So there's not a lot of things basically talking to these compilers that can make highly efficient, deep neural network firmware. So that's why from a CERN initiative and from these high luminosity LHC constraints we knew we would have in the future, we designed libraries designed to take machine learning models, either deep neural networks or decision trees, pass them to our libraries, And then basically they can be used to translate those models into C++ code that you can give to a compiler and then translate into firmware in really, really easy and simple steps that physicists, for instance, can use. And the way it works in detail is that you start with some model that you have, either in Keras, TensorFlow, PyTorch, or ONNX. Then you have to reduce the size of that model using some libraries that I'll talk about later on. Then you pass those models to our HLS-FRML library or Conifer libraries. We will then convert these models to some internal representation that we have. And we will then write basically the C++ code for you, decorated with the right directives targeting a specific compiler. We can then emulate that C++ code to really check that it's doing what it's supposed to do and that it agrees with the model you gave in, all nicely in a Python wrapper. And then you can actually synthesize that model and generate the firmware, resulting in either a co-processing kernel, so you can use an FPGA to basically speed up your inferences, just connected to a computer. You can get a custom design, which is what we do in the triggers. You get some VHDL code that you integrate in a full system, or you can even print an ASIC. So here you can see an example of how easy that can be done. Here you have a small convolutional neural network and some example code of how to load that and pass it to HLS-FRML and build the firmware. So you just load the model, you build some configuration, like how parallel you want that model, and if you want it to be fast or use less resources. Then we convert it to our own internal representation. We write the C++ code that we then compile, and then you can check all in Python, and then we run the synthesis generating the firmware. And here on the right, you can see exactly the same model, the floor plan of that model on the FPGA, so mapped onto the resources on the FPGA. Now, two things to notice on this plot. One is that everything needs to be fully on chip. So whereas in some cases, you maybe can store some of the model weights and parameters off chip on an external memory, we don't do that simply because the latency overhead involved with transferring data back and forth is too high for what we're willing to pay in our system. And so everything needs to fit within the available FPGA resources. Secondly, already with kind of this small model, we don't know how small it is, but it's quite small. Even with this small model, you're filling the full FPGA. So that's why I was alluding to before, is that you need to do something to the model before you pass it on to us. So neural networks are basically multiply and accumulate operations. So here you can see an example. For instance, you have a weight multiplied by some input plus a bias and an activation function applied to that. So for a rather simple network, you very often get into a high number of multiplications. So for this small model with 16 inputs, 5 outputs, you have 4,000 or so multiplications. And the number of dedicated units you have for multiplication on an FPGA is only like 4,000 to 6,000, something like that. So even with this small network, you're basically filling the full FPGA. So the bottleneck basically becomes the number of multiplications you're doing in these deep neural networks. So one of the crucial aspects is that whereas you ideally would like to deploy a huge transformer on your chip, you can't. You're limited by what you have, and this is the reality. And it's kind of the same thing as for ChatGPT. Like, fine, they can buy 11 GPUs, but they still have latency, then making them all talk to each other. It's expensive, etc. So it's becoming more and more a thing of doing efficient inference to really be able to fit things on a single device. So to do efficient inference, there's 3/4 things you can do. One of them is quantization. So we talked about it a bit before. You really need 32-bit floating point precision. Another thing is pruning, so removing small or insignificant connections or weights in a neural network. In parentheses, you can also try to do knowledge distillation, where you train a large network and you try to distill the knowledge of that large network into a smaller one, and also parallelize. So all the computations that can be done in parallel, you do in parallel. And today I'm only going to talk about quantization because it's one of the most powerful things you can do. And with modern tools, it's also one of the easiest things you can do before deploying anything on chip. So we talked about GPT before, where training is basically done in floating point 32 precision. So you have a really large dynamic range. You can't really see this from this plot because usually deep neural network weights are kind of centered around 0 and between -1 and 1. You have a really large dynamic weight with floating point 32, and it's really, really granular. We saw the example before of changing floating point 32 to floating point 16, where you can really reduce the memory consumption of a single model. But on FPGAs, we do everything in something called fixed point precision using fixed point arithmetic. So fixed point arithmetic is way more efficient than floating point arithmetic. It saves you latency and it saves you resources. So you basically put all the numbers into tiny little buckets. So here you can, for instance, see the same weights as you saw before, put into tiny buckets. So you reduce the numerical range and you reduce the granularity, basically. So you have, it's represented like this. You have a fixed amount of digits before and after the decimal point. Now, obviously, if you train a deep neural network and then just put the numbers into buckets, it's by definition lossy. And if you do this, if you keep reducing the bit width, put it in coarser and coarser buckets, at some point you use all the power of your algorithm. So it's by definition lossy, and you really need to tune this precision. So you can ask yourself, can you do better? And this is something we wanted to optimize before we started deploying our own deep neural networks on our FPGAs. And we worked together with Google on something called quantization-aware training and a full framework to do that painlessly and smoothly. So in quantization-aware training, you do sort of kind of co-design of hardware and software. So you train your deep neural network in software, but you already know what the precision of that network will be on the hardware. So during the forward pass, the weights are already quantized to what you know you will have on hardware, say fixed point bit width of 4. Then during back propagation, you do everything in floating point, you tune everything, update the weights, everything in floating point. For a technicality, this quantization operation is non-differentiable, so it's replaced by the identity function. It's something called the straight-through estimator. And then you just redo this loop. You forward pass, quantize the weights, back prop, floating point, and then you go around the loop. And we worked together on a way of doing this really, really simple to design these quantized models. So here you can see an example of Q-keras, quantized keras models, where you simply replace the dense layers with you put a Q in front of them, and you pass the quantizer you want. For instance, a bit width of 6 here and 0 integer bits. And in that way, your network puts the weights in their natural buckets that they will lie on in hardware. So you also want to choose the right quantization. How do you know a bit width of 6? So we also allow you to optimize that for per layer, per weight, per bias. So through a hyperparameter optimization using a library we designed called AutoQ, you can optimize the model based on both the model accuracy as well as the size here in bits. And you can find this Pareto frontiers of the models that kind of optimize / minimize most of them. And you simultaneously can scan over the quantizers and also through the how many filters or how many neurons you want to use in the model. Because as you quantize the model, the most optimal number of filters might change. And here you can see the benefit of quantization-aware training. So this line here, purple, is the example we saw before. You train your model, then you quantize it after training. That's basically what was done also for GPT. They trained in floating point 32, I think, and then reduced to floating point 60T at inference time. And here, using quantization-aware training, you can really reduce the bit width down to 6 bits with no loss in performance. So you can maintain high accuracy. What this does to the resources is more drastic. So you can see here the DSPs, these really limited resources we had, are reduced roughly by a factor of 50 at 6 bits. So now you can either fit a way bigger model, or you can at least fit at all on the FPGA in question. So this is really, really powerful. Now, I just also wanted to mention that we do cater for people who use PyTorch as well. So there's a similar library for PyTorch called Brevitas that also does quantization-aware training. And we're currently collaborating with the Xilinx research labs to develop a common representation, a common format for these Q-keras and Brevitas models. that both libraries can export into and that we, HLS4ML, can then consume in order to streamline everything. Then a little personal note before we move on to examples. And that is that now in this kind of transformer, geometric deep learning, graph neural network hype, we kind of stop thinking about the simplest option. And oftentimes in high energy physics, our data doesn't require these type of models. So we often have tabular data, for instance, and we do see that tree-based models still outperform deep learning on typical tabular data. So one of the first things to do to reduce latency and size, I would say, is always try a decision tree first. So here you can see an example of a deep neural network and a decision tree for a specific task. This is now already quantized to 6 bits. The accuracy is almost the same between the two networks, whereas the latency is reduced from 40 nanoseconds to 5 nanoseconds for the BDT, and the resources are also significantly reduced. And we're currently working together with Google on integrating support for their TensorFlow Decision Forest library to seamlessly talk together with our library Conifer, so you can design really state-of-the-art great decision forests and put them on FPGAs. Due to all of this development that took years, it's now sort of bear fruits, and that's the reason that has allowed us to be at this stage where you see here we have over 20 boosted decision trees and deep neural networks, each of them represented by a stamp here of our logo, in the level 1 trigger plan for high luminosity LHC. And this really wouldn't have been possible without libraries like HLS4ML and Conifer. And there's only a subset of the things. There are way more algorithms currently being developed. So I just wanted to quickly look at a few examples of that. So here you can see the tracking, this system dedicated to do tracking. So we're now looking at how we can use machine learning for tracking. So we have to, from 1,000 or so hits from hundreds of tracks, you have to do accurate track reconstruction within 5 microseconds. And here we're looking at using graph neural networks for fast charged particle tracking. So I also really like this comparison on the bottom. You can optimize your deep neural networks differently, either to be as fast as possible. So here you can see the latency of a throughput optimized algorithm. The cost of being throughput optimized, low latency, is that you use all of the resources available. Now, if you're in a different situation, you can afford to be slower, but you don't have a lot of resources, you can optimize differently using HLS4ML accurately, which allows you to really optimize for your use case. We're also using machine learning in the high granularity calorimeter. There's a lot of R&D on that. So I don't know if you remember, we had this data we sent out that now arrives in the level 1 trigger. Now we still just have basically energy cells. We don't know what produced them. So we're looking at graph neural networks that can detangle all of these energy deposits here. Detangle them using GNN, resulting in disentangled showers from individual particles, all within 3.5 microseconds. And what I think is really, really cool here is that the people actually doing the study contributed back to HLS4ML, wrote their own translation of their graph neural network layer. And this is really how it works for us a lot. There's a big community effort trying to build up this library. We also now combine information from all of the subdetectors. For instance, now we can look at these, try to identify what these quarks are. So quarks generates showers, it generates a shower of outgoing particles that we then cluster together, and we can try to identify what generated that shower of particles. One of the cool things here is that often in our problems, we have permutation and variance. It doesn't matter where these particles are with respect to one another. And we've used graph neural networks and really felt that this is a good thing for particle physics data. But oftentimes we don't only need permutation and variance in our algorithms. We don't really care so much about the edges, so like the information between pairs of nodes. So deep sets is a really cool architecture for that. It basically first transforms each of the inputs by some neural network, then sums it all up, making it permutation and variance, and pass it through a final neural network. And the benefit with these is that they scale linearly in computation time, which really differs from, for instance, transformers that scale really, really poorly. So we currently have a few of these deep set examples running, being done R&D on for the level 1 trigger. Here you can see an example of such an algorithm, a deep set speed tagging algorithm living right next to the algorithm that does the reconstruction of the jet itself. Finally, we also want to be in the system that combines information from all the subdetectors. So we're currently trying to find new particles at the Large Hadron Colliders with limited success. So up until this point, we haven't found anything. So we might ask ourselves whether or not we're looking in the wrong way. And usually when we do searches at the LHC, we start by assuming the standard model and some signal hypothesis, and that defines everything we do in the analysis after that. But how do we know we're looking for the right thing? Now we have this big jungle of new physics theories, and we don't know which one of them are correct. So we need to be a bit more generic. And even our trigger algorithms are designed with some theory bias in mind. So for instance, we know Higgs decays to 4 leptons, and we say interesting events are events with high energy 4 leptons. But we're already losing a lot of data in the level 1 trigger. So is there a smarter way to select events? And what we want to do is, rather than deciding a priori what's interesting or not, is to rather look at the data and try to classify objects and events as normal or anomalous, and then select based on that. And you can use something called, again, autoencoders for that, machine learning for anomaly detection, that trains to compress and then decompress the data. Now, if this is something, if it's a normal standard event, the algorithm will be able to do this rather well because it's seen it a lot. But if there's some data it hasn't seen before, it won't be able to reconstruct the data based on this reduced information. And the difference between the input and output defines a degree of abnormality. So now we rather want to select events not based on their energy, but based on whether or not they're abnormal or not. And this is something we're currently doing in the CMS detector, trying to detect new physics within 50 nanoseconds during these years of data taking. All right, finally, the high-level trigger, where we have CPUs and GPUs. We currently, before, only had CPU nodes, 30,000 of them, 30,000 cores to do the event selection at the high-level trigger. We've equipped all of them with GPUs in order to offload resource-intensive computation. So we have 30,000 CPUs and 400 GPUs. Now, what we want to do is offload some of the tasks from the CPU to the GPU that are time-consuming and run faster on GPU, and transfer the data back and do the rest. And in the future, we want to do up to 80% on these GPUs. Now, particle flow is one of these highly accurate algorithms that you saw before, and it's really, really slow. So we can't run it on all the events, currently only 17% of the events. Now, one of the things we're looking into is using graph neural networks to fastly approximate particle flow. And here you can see an example of classical particle flow versus the graph neural network equivalent, and they have almost the same performance. And the benefit of that is that we now have algorithms that run natively on GPUs. So we don't have to transfer the data back, and we can accelerate this processing even further. All right, so out of the interest of time, since I started a little bit late, I will skip some of the last slides and go straight to a few examples of high HLS FRML and other CMS CERN experiments. So it's not only in CMS that I gave examples from. We're being more and more used, for instance, in NA62 that measures really, really rare decays of kaons, and they have an FPGA-based trigger. We're also being used in Atlas for real-time energy reconstruction and muon position and angle regression. And not even only in particle physics. We're also being used a lot outside of HEP. So for instance, for self-driving cars, we have examples of semantic segmentation based on HLS FRML. We have brain implants to predict epileptic seizures, neural networks for quantum control implemented using HLS FRML, and a lot of different examples you find on the bottom of the page. So I hope this has encouraged you to join the community. It's a really, really nice and vivid community. You can sign up to our e-group. We meet every week, and we have our monthly meeting every 4 weeks or so, where we discuss fast machine learning in the broader science community. Thank you very much.
Thank you, Thea. That was a great, great talk. Okay, people, audience members, questions for Thea? Okay.
Sorry for the rushed ending.
No, that's fine. That's fine. So we have there was one question on the Slack about what is the typical memory that you have in one of your FPGA devices?
Usually we have 16 kilobytes units, 2,000 of them, something like that.
Right.
But it really depends with which FPGA you go for. So that's kind of the typical one that we use in our level 1 trigger. So 2,000 units, 17 kilobytes.
Okay.
Yeah.
So there's another question about whether can you compare HLS4ML and Conifer?
Yes, they do two different things. Well, they target two different things. So HLS4ML is for deep neural networks, and Conifer is for boosted decision trees. But the idea is exactly the same. It just depends on what your algorithm of choice is.
And let me follow up on that. And the performance you get on the FPGA for the two different quantized models is equivalent or comparable?
It really depends on the problem. So in this case, the data is sort of tabular. It doesn't have a structure that needs to be understood. It's basically just a tabular list of information. And then the two perform similarly. It's really just if you have a problem that requires more knowledge about how like more pixelated information, for instance, that you maybe want to use deep learning. And so it really depends on the problem. But I always, if you think you have tabular data that doesn't require this pixelated information, I think it's good to always start with that.
Yeah.
So go back to the basics. I think that's like the goal.
So there's a question, how do you guarantee the efficiency of the design that is generated automatically by HLS4ML?
You don't. It's basically us trying to do what we think is the fastest possible. So in most cases, the operations you do in a deep neural network, they're basically the same. It's a multiplication plus a bias and an activation function. And we just try to make the fastest implementation of that layer. Now, if you would really go and hand tune every little thing yourself, you most likely could make it faster in inference time, but not faster in development time, because then every single time you change the network, you have to go back and fiddle again. So it's sort of a trade-off of fast dev time, get the best you can with fast developing time.
Has there not been any attempt to convert that into a machine learning problem? And
that's a good task, yeah.
Or at least an AI problem. Yeah.
Yeah, you're right.
So there's a question, can you compare the different experience with the different HLS tools from Mentor, Xilinx, and Intel?
Well, it really depends what FPGA you have. So for us, we use the Xilinx tools because we have Xilinx FPGAs. And for Xilinx, they have both Vitis and Vivado, with Vitis kind of being the replacement of Vivado. So there's not so much to choose between. So it really depends on the hardware you have at hand. But I mean, from our side, I can compare how much we support the various things. So currently, since we started within CMS, our libraries are mostly targeting, well, not mostly targeting, that's wrong. We're targeting everything, but we have most support for Vivado and Vitis, just because that's what we use most. So we're trying to catch up for the other backends. Right. So most of the things are supported for Vivado, and it's coming for the other backends.
And do you find that there's a benefit from having a homogeneity in what just the FPGAs that you're actually using, or does a heterogeneity make things more complicated?
I've never been involved with a system that has a connection of FPGAs from different vendors. I would only think that would make it more complicated. I wouldn't see a benefit in combining different types.
Unless you have multiple purchase cycles and one's cheaper one year and the next one is cheaper the next year.
That's true. That's a good argument. Yeah. But that I have no experience with. No.
Right. Okay. Okay. If there are
may I ask one question?
Please go ahead.
Yeah. So hi Thea. Why don't you use point process for triggering your events? There are something called point processes where a self-excitatory process where one process is kind of trigger the other process. So you have shown some events, right? Like there are some events going on, and so why don't you model with point process?
I mean, anything that's dynamic, if that sounds like it's something that's dynamic, basically. We don't want anything that's dynamic in our system because everything is on a really tight clock. So even if, because that sounds like something that would just trigger the next thing, so it could start immediately. Now, in our system, we can't have that because everything is on this tight clock. So there's no flexibility and no gain in basically speeding up processes.
Okay, then how does your variational autoencoder help the time thing, the tight coupling? Because all you are doing is just embedding in some low dimensional space, right? So how does that fast thing come in variational autoencoder, other than disentanglement of the different processes?
It doesn't help with timing, it just helps you compress the data size. And now I show two different examples. One is to compress the data itself so that the size of the data we have to transmit is smaller because we have a throughput limitation. And in the second use case, it's really using it as an anomaly, an outlier detection algorithm. So two different tasks, but not there to help with the latency.
And these two are not synced, like one is the space embedding and another is the time process. So like these two are kind of correlated, or they act in differently, like can you add it at the end?
Of these two autoencoders, or maybe I didn't understand the question.
One process controls the latency, right? And I don't know, maybe some LSTM or RNN kind of model will help that. The other you have shown in your slide is variational autoencoder that only cares about embedding, and this has nothing to do with the time. So I wonder if you are running these two models, let's say for, I don't know, for some task, how this space and the time are you doing together? Are you storing the, like some process somewhere and then do it in your LHC? Or like, I don't understand, because these two are kind of different. How are you carrying these two things together?
Maybe I don't understand the question completely, but we can maybe take it offline because I think I need yeah. I don't think I understand the question completely. The two examples I gave are decorrelated from each other. And the reason we're using that type of algorithm is because it's a very simple stack of dense layers. And in many cases, we can keep only the encoding part. So the architecture is really efficient and small. And it's been good for our problems. But please send me a follow-up email if that's with the full question, if that doesn't answer it.
Great. Okay, thank you, Thea, very much. So Thea's talk will be on the A3D3 YouTube, and the slides will be available as well for those who want to replay and study in greater depth. And she says she'll answer any questions as well if you have follow-up questions. So again, Thea, thank you very much. This has been a great
Thanks a lot.
very enjoyable.
Bye, everyone. Thanks
okay, everyone. Thank you. That's it for this time.
Bye-bye.